I haven't had very many requests for tutoring in statistics over the years. It doesn't really lend itself to tutoring very well. But once you get into probability, probability is pure math, incidentally.
Yeah.
Statistics is not, but statistics uses probability, kind of like physics uses calculus. Calculus is the pure math, so is probability. And I tend to favor subjects like that because I don't really care for subjectivity. When you look at statistics in general, there's a lot of subjectivity there. There's seldom an exactly correct answer. So, factorials. You know what 8 factorial means?
No.
8 times 7 times 6 times 5 times
yeah, okay.
3 times 2 times 1. Okay?
Okay, yeah.
So if I had 8 factorial divided by 7 factorial, what's that going to equal?
Oh, look at that's...
Don't do it on your calculator. I want you to understand this.
2?
No? What if I went up here? That's 8 factorial. Well, 7 factorial is this.
Is it 8?
Yeah. In other words, that part cancels with that part. So you're left with 8.
Okay.
Okay. Now, let's talk about combinations and permutations. Wow. Oh, man. I got to find a different drawing program. This thing just is not liking what I do with it. Well, if I said to you, NPR, you know what that means?
No.
It means n factorial over n minus r factorial.
Okay.
And this is where probability comes into play. Okay, if I say NCR, both of these are big in probability. This is referred to as N pick R, and this is N choose R. Well, N choose R, same numerator, partly the same denominator, but in the choose part, equal number of n's, equal number of r's. So I need an r factorial there also.
Okay.
Okay. Memorize those two. Now let me test you. For pick 3, r is always going to be less than n. Always, 100% of the time. What's that? Once again, without a calculator. I know you can do these on a calculator, but you kind of need to understand them, especially if you're going on to more advanced math. Once you get into calculus, you definitely need to know how to do these without a calculator.
Is it just 4?
Well, it's 4 factorial. In other words, I don't really want an answer. I want you to give me the layout. What's that?
So it'd be 12.
What's that?
12.
Do it again.
Oh, 24, sorry.
Okay. Now let's do 4 choose 3.
be 4 over parentheses 4 minus 3.
4
4 factorial.
Over
4 minus 3 factorial.
Which is 1
3 factorial.
factorial times 3 factorial. That's equal to what?
4.
Yes. In other words, whenever you're looking at something like that, start with the bottom. The bottom eliminates everything but the 4 in the top.
Mm-hmm.
Okay, what's this equal to?
0.
1, by definition.
Oh.
And like, for instance, if you had 4 choose 4, that would be 4 factorial in the numerator, 4 factorial in the denominator times 0 factorial. Well, that's equal to 1.
Okay.
0 factorial is not 0, it's 1. It's kind of like 0 to the 0 power is 1.
Mm-hmm.
Now, most of my life, I've always gotten this sneaking suspicion that they do this out of convenience. In other words, that's the only way everything works, is if they make 0 factorial equal to 1. Truly, that's what I thought for many, many years, was that it was just accepted by mathematicians because if they didn't do it, none of these equations would work. So you have to make 0 factorial equal to 1, and 1 factorial is also equal to 1.
Okay.
Now, I no longer believe what I used to believe, that it was done for convenience, any more than 0 to the 0 power. That's actually equal to 1.
Mm-hmm.
It's not done just for convenience. And I suspect the same is true with factorials. Now, there we go. Figured out how to go to a new page. What do you think this is equal to?
50 times 49 times 48, etc.
What do you think that answer is? Take a wild guess. Seriously, try to give me your best guess.
Jesus.
I know it's hard.
Probably in the hundreds of thousands. I don't think I can give you a best guess. Oh, it's mathematical notation.
No, it's
Or
just,
scientific notation.
no, that's not hundreds of thousands. That number is more molecules than are in the entire universe. There are only like 10 to the 50th molecules in the universe. Every planet, every grain of sand on Earth, every grain of sand on every planet in the entire observable universe has less molecules than 50 factorial. It's always amazed me that 50 factorial is this big of a number.
Yeah.
I can't, that's not a Google. A Google is 10 to the 100th power. But, you know, if you want some feeling as to what that is, it is a gigantic number. Now, here's an interesting question. I know you don't know limits, but you should understand this. If I have x factorial in the numerator, and I have 2 to the x power in the denominator, in other words, I have factorial growth taking place in the numerator, and I have exponential growth taking place in the denominator. Which one wins? In other words, which one grows faster? Is the limit of that going to be 0 or infinity? If the bottom grows faster than the top, it's going to go to 0. If the top grows faster than the bottom, it's going to go to infinity.
Wouldn't the top grow faster?
A lot. Okay, well, let me give you another problem.
Top would still grow faster.
No matter what this number is, I can make that number 10 gazillion, and eventually the top would outrace the bottom. It would take quite a while. In other words, this doesn't go faster than the top if x is 2. If x is 2, you have 2 divided by 4. The bottom's bigger. But the moment x gets to be 3, now you have 6 divided by 8. Bottom's still bigger. But when x is 4, you have 24 divided by 16. All of a sudden, the top starts to get bigger. And it just increases its lead. So the essence is that factorial growth is greater than exponential growth, no matter what the base. The limit of this thing is, in fact, I could even, no, if I say x to the x, that changes everything. But that's another story. Some of this stuff probably is not going to necessarily apply to your statistics stuff, but maybe I'm going the wrong way. I am. Okay. Do you have any specific problems you'd like to go over? I think we've covered factorial pretty good. Well, hold on. Let me add one thing.
Okay.
And that is, when do you use permutations, which is this one, and when do you use combinations, which is that one, in probability? Permutations, order matters. Combinations, order does not matter.
Okay.
Play cards.
Order matters.
If I give you 2 cards, let me see how I can explain this. Do you play poker at all? You know what a flush is?
Yeah, I played poker.
Okay, so you know what a flush is.
Yeah.
So if I have a flush and I have the ace, queen, 3, 4, 3, 2 of hearts. Does not matter what order those come in, right? In other words, I could have the queen, 4, 3, 2, ace, and I have the same hand. Both of those are the same poker hand. They're ace, queen, flush. Ace high, queen next, flush. So I don't care whether I get the ace first or the ace last. Because all I care about is the 5 cards are these 5 cards. So this would be a combination problem. And I think the odds of getting a flush would be 13 choose 5. In other words, if I were to deal you 5 random cards from a deck of cards, the odds of getting a flush would be this. And order doesn't matter. However, if I said, what's the odds that I get precisely ace dealt first, queen dealt second, 4 dealt third, 3 dealt fourth, 2 dealt fifth, well, that's 13p5. And we've already seen that that's a much bigger number. That is that number. This one down here is 13 choose 5, which is 13 factorial over 8 factorial times 5 factorial. That clearly is a smaller number, as it should be. In other words, we certainly can know that it's much harder to get ace, queen, 4, 3, 2 dealt in that precise order than it is to just get any 5 hearts that contain those 5 cards. It's got to be greater odds, or rather more likely to get dealt a flush in any order than in a precise order. And when you're playing poker, it's any order that matters. You don't care if you get it dealt queen, 4, 3, 2 ace or ace, queen, 4, 3, 2. They're both the same hand. So if you're trying to figure out what are the odds of getting these 5 cards in a flush, then it's a combination problem. It's not a permutation problem.
Yeah.
You want me to give you some simple probability problems?
Sure.
There's 5 ladies. They're going to randomly sit in 5 chairs. How many different ways can they sit in those 5 chairs?
25. Or no. Bigger than that, isn't it?
Yeah. First of all, does order matter or does it not?
Order doesn't matter.
Actually, it does.
What?
Yeah. This is a case where order matters. How many ways can lady number A sit in the first seat? This is a little different than permutation and combination, but it's still probability. And this is a classic.
5 ways.
This is a classic probability problem. 5 ways, right?
Mm-hmm.
Okay. Now, how many ways? That's lady A. How many ways can lady B sit in the second seat?
5 ways.
4.
4?
Yeah, lady A is already in the first seat. There's only 4 people left. There's 4 seats left. So for B to be there, there's only 4 ways. For A to be there and B to be there. And, yeah. So
5 factorial.
the different number of ways they can actually sit is 240 ways.
Okay.
Okay.
I understand. Okay.
Yeah, you could have A there, B there, or you could have A in the second slot or A in the third slot. So there's 5 different ways that A could sit there. Now that is a permutation problem. And I believe it would be 5 permutate 1, which would be 5 factorial over, no, must be 5. Wow. That's difficult. I'm not quite sure how to write that as a permutation problem. Giving you a little bit of probability all the way around here. Do you have any specific probability problems you wanted to cover today?
Not really. The
Okay.
only thing I was unsure about is factorials.
Okay. Okay. Let me ask you a few more questions. For some reason, when you scheduled a session today, I figured you probably had hit probability.
Yeah, we did.
Because I don't see you needing tutoring when you're in statistics, the part at least that doesn't have probability as part of it. In my book, statistics is part 1, part 2, and then part 3 is probability, and then part 4 is back to statistics. So 1/4 of my book is probability, 3/4 is statistics. And I figure you might need help with probability. Probability is a tough subject. It really is. As much as I love probability, and I've spent my whole life playing games of probability like poker, gin rummy, backgammon, anything that has probability assigned. I was going to say chess, but chess doesn't have probability. Not really. Chess is precise and exact. There's not a lot of probability in chess, but there's a ton of probability when you play no limit hold'em. And you better know your probabilities if you're going to be a good player at that. So I consider probability one of the most important subjects in the world. I really do. It's just it's not one of my strongest subjects. I have difficulty with it. It's that hard. I'm easier with calculus than I am probability. Now, probably because I haven't tutored a ton of probability, whereas I've tutored a ton of calculus over the last 8 years. But nonetheless, probability may be the more interesting subject. The world runs on probability. It does not run on predetermined. In other words, when you examine the quantum world, do you know much about quantum physics?
Not really.
Quantum physics is ruled by probability, as opposed to regular physics, the physics of the large or medium. That's not ruled by probability so much. If there's a 10-mile wide meteor headed towards Earth that's not due to hit us for 30 years, guess what? That's hitting us. There's no probability involved there. The only probability might be, is there another meteor coming at a different angle that might hit that meteor, knock it off course so that it wouldn't hit Earth. But if you could see the positioning of all the planets and meteors, and you knew that this meteor was headed towards Earth and nothing was going to hit it before it hit Earth, that is 100% predictable. They would know that 30 years in advance if they spotted the meteor in time. Now, there's a lot of meteors that they don't spot until they're a year away from Earth. So we could always wake up one morning and there's a meteor headed towards Earth that's going to hit us in 6 months, and nobody has spotted it yet until this morning. So when you're dealing with large objects, everything is predetermined. There's no probability involved. But when you're dealing with small things that have atoms and electrons, and you want to know where an electron's going to be at any moment in time, that's pure probability. It is nothing but probability. In fact, quantum physics is freaky about probability. And I mean freaky. I once heard somebody say that there might be a few thousand people on the planet that truly understand relative physics. Einstein's relative physics. But there's nobody on the planet that really understands quantum physics. It's that hard to understand. And it's because it's entirely probability ruled. And when you go up and you deal in larger things like any kind of a gaming proposition where you're playing cards or you're rolling dice or anything like that, you can see the probability aspect in the short run, but it's guaranteed as to what it's going to do in the long run. If you flip a coin 1,000,000 times, you're going to be really, really, really close to 50% heads and 50% tails. But if you flip a coin once or twice, you could get anything. You might get 2 heads or 2 tails. You're not going to get, most likely, 50-50. Certainly if you flip it once, you don't get 50-50. You get either heads or tails. And every flip is independent of the previous one. In other words, the coin has no memory, okay? So now you work out the logic for me as to how come if I flip it 1,000,000 times, I'm going to approach 50-50 if the coin has no memory. And yet that is the truth. It's called the law of large numbers with probability, which says that as your sampling interval increases, or I should say sampling universe, in other words, if you flip a coin, let's say you flip a coin 100 times, you might get 52% heads, 48% tails. Entirely possible. If you flip it 1,000 times, you might get 50.5% heads and 49.5% tails. Entirely possible. You flip it 1,000,000 times, and this thing is going to be like this. In other words, what the law of large numbers says is that the greater your sampling universe, the closer it's going to come to its true theoretical probability, which is 50-50. And the smaller your sampling universe, you can get results that are significantly away from that. If I flip it 10 times, I might get 70% heads and 30% tails. If I only flip it 10 times, that wouldn't be that hard to do. 7 heads, 3 tails. So this law of large numbers is one of the more critical theorems for probability. The greater your sampling universe, the more accurate you're going to be. But it still begs the question that I asked, that if the coin has no memory, how does it know? That's what probability is all about. It's undeterminable. It is a probability. And there's a lot of views on the universe that the entire universe operates on a probabilistic model. So that you never know exactly what's going to happen in the future. It's undeterminable. Whereas back in Sir Isaac Newton's age, before they discovered quantum physics, he believed everything was predetermined. Had to be. You have a molecule and it's going in a certain direction and it's going to collide with another molecule. There's only one thing that can happen. Only one. So Newton's laws, his physics, said that everything in the universe is predetermined until quantum physics was discovered in the 20th century. And then now it kind of looks like everything in the universe is probabilistic. So probability is a great subject. It really is. And I've read the probability part in the book. So if you do need help with specific problems on probability, please feel free to schedule a session. And if you don't need help on the statistics, now I will say this, that once you get past the probability part, the statistics part gets harder and harder. So you may actually need help on the statistics part even when you're done with the probability section. At least that was my feeling as I read the book. Once I got past probability, then they really start getting tough statistics. Cole, I will let you go.
All right.
And I will plan on seeing you next Thursday. I tell you, yeah, that's fine. I was going to say that, you know, if you reach a point where you just don't feel like you need tutoring on statistics, let me know and I'll take you out of this as a permanent time slot. But
all right, sounds good.
I'll leave it there for now because you're going to be studying probability for a month at least.
Yeah.
And you might need help there. And I would love to give you help with probability. I would love to actually tutor some probability since it is a pure math. All right. So I will plan on talking to you next next Thursday at 5:30.
All right, sounds good.
All right, cool. Bye-bye.
Bye bye.